Right. Welcome to 2.5, which is the delta function potential. Before we actually get into this, we have a little bit of nomenclature that we want to sort of start classifying before we get into actually solving for this kind of potential. So as a quick review, so far, what we've been doing is we've been basically solving Schrodinger's equation by using the method of separable variable separation, effectively. So what we mean by this is that we have a solution psi of x comma t, and we're assuming that it can be separated into a time-independent solution psi of x multiplied by a time-dependent solution phi of t. And we've done this for three different sets of potentials. We've done this for the infinite well, which looks, something like this. We've done this for the harmonic oscillator, which looks, something like this. And then we've done this for the free particle, which is just, v equals 0 everywhere. So what we've seen is that the separable solutions obtained when solving for these two top solutions, the infinite well and the harmonic oscillator, these result in psi of x that is normalizable and quantized in E. So what we mean by that is that, first off, the stationary state solutions for both of these types of potentials are normalizable, as we've seen, and also they result in sort of energy values that sort of take on discrete values. The energies aren't continuous. Particles that are in stationary states in these sorts of systems cannot take on a continuous spectrum of energy. There are very distinct levels of energy that particles jump between. And we sort of saw that that was one of the requirements for stationary states as well in the first place. So the whole point of solving for a stationary state is, or one of the requirements for even being able to solve for a stationary state in the first place, is that sort of k, which is directly related to the energy, has to be quantized, and therefore energy has to be quantized. So we ran into these two initial sort of potentials without any problems, and everything agreed. Then we ran into the free particle, and we found that for the free particle, psi of x is not normalizable, and is continuous in E. So the difference between the free particle and the two other systems up above is that sort of the energy is continuous, and because of that, and that comes about because of the fact that, remember, there's no boundary conditions for the free particle to sort of impose quantizations of E, as we've seen, since V is just equal to 0 everywhere. And what this means is that since the energy is not discrete, that violates one of the requirements for being able to solve for stationary states in the first place. So because of that, the stationary states that we do get from the free particle are effectively not realizable. They're not actual solutions. They will never happen in real life because there's this conflict that's happening where we're trying to solve the system using a method that requires continuous, or not continuous. We're trying to solve this system using a method that requires discrete values of energy, but one of the first things we discovered was that this system actually does not have discrete values of energy. It has continuous values of energy. Now, regardless of whether or not sort of the stationary state is realizable or not, in all three cases, we sort of solved for psi of x comma t, which is the more general form that depends on x and time, via the completeness theorem, which basically said that we can express this as a summation indexed by n from 0 to infinity of some coefficient Cn multiplied by psi n of x multiplied by phi n of t. And we saw that even in the case of the free particle, where sort of the stationary states aren't actually physically correct solutions, sort of this completeness theorem idea still holds, and we can either use Fourier transforms in the case of a free particle, where the energy values are continuous, or Fourier's trick in the infinite well and harmonic oscillator, where we have a continuous energy, to sort of manipulate these variables around and sort of find the coefficients Cn when given psi of x comma 0 in order to build up psi of x comma t in the general solution form. So that's all fine and good, but physically there has to be some sort of distinction between like these top two sort of station where the stationary state is physically realizable, and this bottom one where the physical where sort of the stationary state isn't physically realizable. And it turns out that this is one of the things that sort of carries very well over to classical mechanics. It's very easy to sort of make an analogy for why this difference is happening. And what I mean by that is we have to introduce things called bound states and scattering states. So in classical mechanics, typically when you're dealing with, when you're being introduced to things like potential, one of the first things that, or one of the earlier systems that you get introduced to is something like a potential well. So let's say that I just, instead of using something abstract like potential, let's use something a little bit more concrete. And let's say that, for example, I have a ball and it's sitting at the bottom of like this valley. And let's suppose that I'm marking points in height. So this is at y equals 0, and this is at some value y equals h, whatever the height of the valley is. So what happens here is that I can characterize the energy of this ball. So the ball has energy 0, obviously, because it's on the ground and it's not moving. So energy of the ball is just equal to 0. In contrast, if I had, a second ball, like, or, you know what, instead of a ball, I have like a person up here at the crest of this hill, then the energy of the person, well, he's stationary, so he has no kinetic energy, but he has some gravitational energy, and that's going to equal m of the person times g times h. So what happens here is that this ball is sort of stuck inside this well, and if I want this ball to not be stuck inside this well, I have to give it some kinetic energy that is greater than sort of the potential energy that the ball would have sort of at the peak of the hill. So you know what, this is actually not, because of the fact that like the masses of the person and the ball are different, let's instead just use a second ball. I don't know why I tried with a person. That's not necessarily, doesn't really work very well. Let's say that this is the ball in case 1, where it's stuck stationary at the bottom of the valley, and this is the ball in case 2, where it's sitting stationary at the top or at the crest of this hill. So the energy of ball in case 2 is going to be the mass of the ball times g times h. So if we want to get ball 1 to the position of ball 2, we have to give it a kick via some sort of kinetic energy. We kick it to give it speed so that it can actually like roll up the top of the hill. Assume, let's ignore the fact that this is a super steep hill and it's probably not gonna, it's probably just gonna start sliding off due to friction. Let's assume that this is like a sticky ball and there's no, there's no like weird things that are slowing it down. If I give this ball a kick, it's going to sort of move up the slope. That kick is gonna give the ball a momentum. That momentum is gonna carry it up the slope. Whether or not it actually makes it to the top of this hill depends on how much kinetic energy I give it. So the kinetic energy, in order for it to get to the top, the kinetic energy has to be exactly equal to mbgh, which is what we have here. If the energy is less, what will happen is that the ball will reach, some middle point around here, and it'll start sort of oscillating between like two turning points, like sort of a harmonic oscillator. If I give my ball kinetic energy that's greater than mbgh, it's going to make it past the hill. And let's suppose that let's analyze this as like a finite potential well. So suppose that the hill just goes off to 0 after you make it out. So, like this just goes off to infinity. This goes off to like negative infinity. Assume that there's no friction or any air resistance or anything that's going to dissipate the energy of the ball and make it come to a stop afterwards. If the kinetic energy that I give it is greater than mbgh, it's going to make it past the crest of this hill, either direction. Suppose I kick it towards 2. It's going to make it to the point on 2, and it's going to keep on going And it's basically, it's gonna like, it's gonna go forever. It's going to move forward, and it's going to make it past the hill, and it's going to gain speed again. It's going to get to the bottom, and it's going to just keep on moving forever towards infinity. And what we say is that in any system, so looking at this more in terms of abstract potentials again, if I have some sort of potential well, and I have my ball in here, and say this is v equals some constant a at the very top, and let's say at the bottom here this is just v equals 0. If my energy of whatever this thing is, my ball, my particle, whatever you want, if the energy is less than, you know, a, which is sort of the height of this barrier, then this is called a bound state. And I would like to think that this is, the name itself is pretty intuitive. The ball is basically bound inside this localized region, going from, let's say, like negative x to positive x. It's sort of stuck here. It can never leave the region. And remember, this is still, we're still dealing with classical mechanics. We haven't gone to quantum yet. Now, if the energy of the ball is greater than a, then, you know, I'm gonna have like the ability, this ball is going to have the ability to sort of break out of this well. In the case of sort of this, how do we call it? In the case of this slope, the energy that allows it to break out is going to be kinetic, because that allows the ball to roll up the slope and over. In the case of something like this, where it's like just two flat walls, the potential that bounds the ball inside is going to be more based on like, you know, like the structural integrity of the molecular bonds of like whatever my walls are made of, but that's getting a little bit too complicated. So simply, in simple terms, if E is larger than A, where A is sort of the value of the potential walls, this is called a scattering state. And hopefully this name is also intuitive, because what that implies is that, you know, if there's a scattering state, the ball has, or the particle, or whatever you want to call it, has enough energy to break out of the well that it's confined in, and it then just goes off to infinity. Because if it has energy greater than A, it's going to have energy left over after breaking out, and the most common form of that energy is going to be kinetic, so it's just going to keep on moving forward or backwards to positive or negative infinity, respectively. In quantum, this sort of analogy applies directly. So sort of, we see here that the infinite well and harmonic oscillator both have sort of potentials that go to infinity. You know, like the infinite well has an infinite potential that goes outside of this localized region. So effectively, if I have a particle, it's going to be sort of localized in this well no matter what. The same thing with the harmonic oscillator. Harmonic oscillator, or at least the one that we've studied so far, is really just like, it's just an infinite well, but instead of having like a square bottom, it has a rounded bottom. So this is the exact same thing. Sort of the particle is localized in this region. It can never get out because the potential is infinite sort of out here. And it can't. It's going to be stuck localized in this area. In contrast to that, for the free particle, this is obviously a scattering state, because, you know, there's no potential barrier whatsoever. There's nothing stopping it from not being able to move somewhere. So it's going to just be able to go wherever it wants. This is a scattering state. So evidently, bound states correspond to stationary wave functions that are normalizable and realizable, and therefore have quantized energy values, whereas scattering states result in stationary states that are not normalizable and thus not physically realizable, and also have continuous values of energy, or almost sort of a spectrum in K, if you will. Now, there is one major difference between sort of quantum and classical, and this actually for once works in the favor of quantum. This property actually makes quantum systems more simple compared to sort of physical, sort of classical ones. Because in classical ones, when we have some sort of very complex potential, so let's say we have a ball rolling on some sort of potential hill, and it's this weird, super complicated thing, and let's say like the ball is like right here. So this is a graph of V for the ball. So whether or not it can, you know, make it out of this hill, or whether or not it can get through sort of all of these dips, either going to positive infinity or going to negative infinity, is sort of a little bit more complicated to actually calculate. because we have to take into account, okay, does it have enough energy to make it past this first dip? In this case, obviously yes, because we've drawn it a bit exaggerated. But if we had something that was a little bit more, even, it would be a lot harder to tell. And then this 2, we have to find like, okay, from this point, does it have enough energy to make it past this second dip, and then keep rolling out to infinity, and so on and so on. So in classical, this isn't necessarily hard, but it is sort of, we have to do multiple steps, is what I mean. We have to analyze each of these individual slopes individually, analyze the energy at each point to see if the ball can make it through each sort of potential barrier, and so on. In quantum, things are sort of, for once, a little bit simpler. And what I mean by that is that there's sort of this thing in quantum mechanics that's called tunneling. And we actually saw this when we were sort of doing problems for the harmonic oscillator, sort of way back in, I believe it was 2.3. What we saw was that for something like, when we drew out the wave function for like a harmonic potential, what we saw was that the wave function, it doesn't instantly go to 0 at like sort of the points. So let's suppose that we have a wave function that looks something like, this. It doesn't instantly like just go down to 0 immediately once it gets to the point where like the potential is higher than the energy of the wave function. What happens instead is that they exponentially decay to 0 instead of like instantaneously dropping to 0. So what sort of that implies is that there's actually sort of a non-zero chance of the particle being found in like a region that's sort of classically forbidden. There's a non-zero chance that I could have a particle like way out here, because like this is an exponentially going to 0 function. It never truly reaches 0. It just gets super, super small. So there's nothing technically forbidden about finding a particle way out here where like the potential is like super high, and like the particle energy is like way smaller than it. It's still technically possible. It's just the probability of it might as well be 0. It's astronomically small. It's astronomically small, but it's not 0. And this idea is called tunneling, which basically, without going into the math of it, we'll sort of derive out the actual mathematics of tunneling later down the line. But the fundamental idea of tunneling is that for any finite potential barrier, so if I have, a V, sort of an X versus V graph, for any sort of finite barrier, so I can have this crazy thing. I can have something that looks like, this, and then like this, some crap like this, and I can have a particle that's going in with some energy. Traditionally, let's say that like let's say that energy equals like energy equals like 0.5, and let's say that the lowest point of the potential is like 200. So like the potential is way higher than the energy. So like classically, the particle would never be able to sort of make it through, and if this was drawn more to scale, the particle would be like super close to the ground. It would be like down here somewhere with like an energy of 0.5, and realistically, or not realistically, but classically, this particle would never be able to make it past this barrier, because the lowest point of this barrier, which is like around like here, has an energy value of 200 joules, whereas this particle just has a constant energy of 0.5 joules. If we were looking at this from a classical perspective, it'll never be able to make it through this barrier. This particle will it'll travel a little bit up the slope, and it'll like slide back down, and it'll go to like negative infinity. In quantum mechanics, the difference is that as long as your potential barrier is finite, there is a non-zero chance that the particle can just go through your potential. And if you were to like draw out the wave function, it would sort of look something exactly like this, where like once it gets to the classically forbidden region, it'll start exponentially decaying to 0. The probability of finding the particle anywhere past the classical region exponentially goes to 0. But the fact that it's an exponential decay means that it never actually reaches 0. So there's technically nothing stopping the particle from just randomly appearing on the right side and continuing to move to the right forever, and making it all the way to like positive infinity. So the fundamental idea behind this is that sort of in quantum, we never have to worry about sort of these systems where there's like a bunch of different potential barriers, and like there's a bit of like uncertainty on like, oh, can this particle actually make it through each of these barriers? Do I have to analyze like each of these cases individually? I have to analyze the particle at the starting point right here, and I have to analyze it here, and I have to analyze it here, or not necessarily here, because if it makes it here, then it's home free. But like having the whole idea of having to analyze the energy at multiple points to see if it can clear individual barriers is not something we have to worry about in quantum. Because in quantum, the whole idea of tunneling is that as long as you have a finite potential barrier, there's a non-zero chance of your particle being able to make it through. So in actuality, what happens is that what we really care about is the potential at positive and negative infinity. Because that is sort of where it matters. Because a bound state is sort of constrained between finite values. So if there's some potential that's going to be always greater than the energy at positive or negative infinity, then the particle is effectively going to be bound forever in a finite region, and it's going to be a bound state. If the potential goes, if the potential is less than the energy at positive or negative infinity, then that means the particle is never truly bound, because even though I can have a bunch of localized super high potential barriers that sort of effectively bound the particle, on a technical level, there's always going to be a non-zero chance that my particle can just get through those barriers via tunneling. And because of that, sort of there's always going to be a non-zero chance that my particle can just go off to infinity and escape all of those potential barriers all the way up to positive or negative infinity. That results in a scattering state. So in quantum, the rule is that if energy is less than V at plus or minus infinity, then we have a bound state. So in this case, you have some potential that's always going to be sort of higher than E at positive or negative infinity is sort of forever going to be bound. Because, although tunneling sort of applies, the fact that there's always going to be potentials that are higher than the energy sort of infinitely far away implies that our particle is going to sort of be bound in this finite region. So that always is going to result in a bound state. We've sort of always looked at realistically, we've always looked at sort of cases where like the potential just goes to infinity far away, because we've seen the infinite well and we've seen the harmonic oscillator. And in these cases, it's pretty cut and dry what's actually, it's pretty easy to understand it, because like if the potential is infinitely far away, the particle is never going to be able to make it infinitely far away. In this case, where you have like finite potentials, is a little bit weirder, but you really have to sort of wrap your mind around like the idea of potential always being bigger than energy at infinity, because infinity is not a number, it's just this concept of like being larger than something. So the fact that E is less than V at positive and negative infinity basically just means that this particle is always going to be bound in some sort of potential well, no matter how far out it goes. So because of that, it's bound. In contrast, if E is less than the potential at positive and negative infinity, this is going to result in scattering. And what this means is that, no matter how far out we go, there's always going to be like the energy of the particle is always going to be, apologies, I just realized I wrote this wrong. It's greater than. So the energy of the particle is always going to be larger than sort of the potential barriers at infinity. The energy is always going to be able to break out without any problem. There's nothing sort of binding the particle to a localized area, because if the energy is just straight up greater than the potential, there's no need to worry about tunneling. It's just going to make it through the barrier every time. So there's nothing stopping the particle ever from going off to positive or negative infinity. So this is effectively a scattering state. Once again, this idea of sort of tunneling introduces a bit of complexity or a conceptual weirdness to the whole idea, because it's like, realistically, there's no such thing as infinite potentials. So like particles, it seems as if a particle is always scattering, because it's always like, it can always break through any finite potential barrier we put. But this constraint is a very strong constraint, because this is basically telling us that no matter how many barriers that we break through, there's always going to be barriers up ahead that sort of constrain our particle, reconstrain our particle. So because of that, this is technically sort of a bound system. Whereas in this case, there's nothing ever, so it's always going to be a scattering system. Realistically, there's no such thing as a potential that doesn't fall to zero at infinity. Potentials, pretty much, with a few very weird exceptions in fringe cases that you'll deal with maybe in like graduate school for physics, you'll never have to deal with a potential that doesn't go to zero at infinitely far away. So more realistically, v at plus minus infinity is always going to equal zero. So what actually happens is that we can simplify this even further and say, if E is negative, then we have a bound potential. And if E is positive, we have a scattering potential. Or not a potential, I'm sorry. A bound system and a scattering system. So effectively, you know, that's what that means. Now, this doesn't correspond very well with, you know, the cases we've studied so far, because in the infinite well and harmonic oscillator, in both cases, no matter how high the energy of the particle got, it was always bound in this well. So that seems to sort of contradict what we've gone here, because E is always greater than zero in sort of those two systems, but it's still somehow bound. And the reason why this problem happens is because in these cases we're dealing with sort of idealized systems. You know, the potentials here go to infinity, infinitely far away. So because of that, sort of this whole idea falls apart, because these are not physically real. It's not physically real. It's not possible to have an infinite barrier that just goes to infinity, infinitely far away. It's not even possible to have like an infinite potential, period, but these do. So these are not realistic. These are idealized systems. If you wanted to look at it in this case, well, for for harmonic oscillator and infinite well, sort of V at plus or minus infinity is actually just equal to infinity. So in those cases, if E is less than infinity, then you have a bound state, and that's exactly what we have. We have quantized values of E that are positive but finite, and E can't be greater than infinity. So for those two idealized systems, it's never possible to actually have a scattering state. But regardless, we're talking about real systems here. So for any real system that has real potentials that can actually be physically achieved, this is the general case. All right, now that we've sort of gone over this terminology of bound and scattering states, we can start going over the actual delta function well. So as a quick review, the delta function, or the Dirac delta function, is basically, it's labeled as a delta of x, and it's basically this function that equals 0 everywhere except at the origin. So it equals 0 if x doesn't equal 0, and it equals infinity when x equals 0. And it also has this secondary property, which is that the integral from negative infinity to positive infinity of the Dirac delta of x dx is equal to 1. So if we graph this, what this looks like is basically it's flat the whole way through, sort of. And then at this point, x equals 0, it just, this is, I'm very bad at drawing something like this, but it's just an infinitely sharp spike that goes up to infinity and then comes back down. And even, you know, this isn't an accurate drawing because it's infinitely sharp. So like it's more like an instantaneous jump as you go from x doesn't equal 0 to x equals 0. The way I draw it here, it looks more like just a really sharp Gaussian curve. That's not what it is. It's an infinitely sharp spike that just goes to infinity at x equals 0. Technically, it actually isn't even a function because it's discontinuous. It's x equals 0 everywhere except, or it's equal to 0 everywhere except at x equals 0, where it just instantaneously just jumps to infinity. So it's discontinuous, and it's not technically even correct to call it a function. But regardless, we call it that, and there's not any particular reason why we call it a function. It's just it's just something that we call it, and it's a very useful term in physics and math. And the reason why is because it sort of acts as this artifact that can be used to sort of pick out specific points. In physics, it's really useful for describing point-like distributions. And I believe Dirac deltas are used most prevalently in undergraduate level physics in electrodynamics courses, because if you want to deal with something like a point charge, you know, at the origin, you would describe like the charge density as a Dirac delta of like R, where like, you know, there is a charge at 0 and there's no charge anywhere else. So like rho, or the charge density, is defined using a Dirac delta. There might be some constant at the front that I'm leaving out, but that's the general idea behind it. In math, it's also used extensively. The reason why it's useful is because it has this ability to sort of pick out points. And what I mean by that is, let's suppose that I had like a function Dirac delta of x minus a. And let's say that I multiplied some actual real function at the front. So what does this do? Well, the Dirac delta is equal to 0 everywhere except when x when x equals 0, or when its argument equals 0. So when x minus a equals 0, or when x equals a. So everywhere other than at x equals a, this equals just 0. So what that sort of means is that this Dirac delta can be used to pick out f of a exactly. So this is effectively the exact same thing as just saying f of a, Dirac delta x minus a. Because once again, at every value other than at x equals a, the Dirac delta function just equals 0. So because of that, all those other values of x just equal to 0, and this sort of snipes out the point x equals a and f of x. Another useful identity for this is that it can be used to sort of, it's even more sort of useful when it's paired with an integral. So what I mean by that, if I take an integral from negative infinity to infinity of f of x times Dirac delta x minus a dx, what this does, first off, this is equal to an integral from negative infinity to infinity of f of a times Dirac delta x minus a. And immediately, you know, f of a is now just a constant that can be moved out of our integral. So this is just equal to f of a times the integral from negative infinity to infinity of a Dirac delta. And we have this property right here, which is that the integral of any Dirac delta is just exactly going to be equal to 1. So this is just equal to f of a. So this is sort of what I mean by that the Dirac delta is sort of like a sniping function that can sort of pick out individual values of things. And this makes it a very useful property. If you sort of take higher levels in math classes, this comes up very frequently. It's a very useful property for doing a lot of very tricky things with it. For now, we are not concerned with any of those. What we're concerned with is the Dirac delta potential well. So let's analyze that. Let's suppose that I have some potential. So I have some potential v of x is equal to negative alpha Dirac delta of x. So what this means is that this is some sort of spike. So if I drew this as a potential well, it looks something like this, where it's 0 everywhere except at x equals 0, where it just spikes downwards to negative infinity, and it comes back up to 0 afterwards. And I want to analyze, you know, a potential. This as a potential. So what is this? You know, this is, in reality, right? We've been dealing with sort of the infinite square well. This is one of the first things we deal with. What the Dirac delta well is just, I'm taking the logical extreme of a square well, where I'm basically just, I'm squeezing the width of this well so that it becomes a well with like a width of, you know, 0, right? And I'm making the well, once again, I'm also making the well infinitely deep. And the other thing I'm doing is that I'm just shifting the well down so that like the top of the well lies on the x-axis instead of being at sort of y equals infinity. But other than that, it's sort of, the whole concept is exactly the same. So how do we solve this? Because it doesn't really make sense to write v of x as this, and the reason why is because it only equals, v of x is only non-zero. If I have a Dirac delta potential, v of x is only non-zero exactly at the point x equals 0. Everywhere else, it's just exactly, it's just equal to 0, because, you know, v of x is going to equal 0 if x doesn't equal 0, and it's going to equal infinity of if x does equal 0. So there's only a single discontinuous point at which my potential is actually not 0, and everywhere else it's exactly equal to 0, which is sort of the case we've always been dealing with when we were looking at sort of the potential well, or the infinite potential well. So what we can do is we can just analyze the behavior of V, or we can analyze the behavior of psi directly to the left and directly to the right of the well. And then we can sort of impose conditions, because remember, sort of the conditions of psi still sort of come up, which is that psi, psi of x has to be continuous. It doesn't make sense for psi to be discontinuous. So there's nothing stopping us from just looking at, psi when x is less than 0, and then looking at psi when x is greater than 0, and then sort of requiring that these two equal each other exactly at x equals 0, and then just sort of stitching together a wave function like that. So let's do that. Let's write this out fully. So the Schrodinger equation is negative h bar squared over 2m times d2 psi over dx squared minus v times, or I believe it's plus v times psi, equals e times psi. So if v is just going to be 0 everywhere except for at infinity or at 0, and I'm not analyzing 0, I'm analyzing all points to the left and to the right of 0, I can just sort of set it equal to 0 and just treat it or solve it in the exact same way I did with sort of the infinite square well. So let's analyze the point where x is less than 0. So at x is less than 0, v is 0, so what we have is negative h bar squared over 2m times d2 psi over dx squared is equal to e psi. If I want to rearrange this, I get d2 psi over dx squared is equal to negative 2me over h bar squared times psi. So normally we define, like, we would define this as like, negative k squared times psi, where k is like, the square root of 2me over 2h bar squared. But we can't do that here. And the reason why is because one of the key idea here is that energy is less than 0 for a bound state, right? And actually, you know what, this is something that I probably should make clear, is that we're analyzing, there's two different ways to analyze this system. There's a bound state where the energy is negative, and then there's a scattering state where the energy is positive. So we're going to start by looking at bound states. So in the case of a bound state, right, just to emphasize that we're looking at a bound state, let's write this down. We're looking at bound states first. So if energy is less than 0, I'm not allowed to just write, I'm not allowed to define k equals 2me over h bar squared, because if energy is 0, then this thing is 0, and k is going to be imaginary, and it doesn't make sense to have an imaginary k, because k is directly related to e. So if k is imaginary, e also has to be imaginary, and that just doesn't seem to make sense. So instead of defining this, I have to define it. I have to define this as positive k squared times psi, where k is now going to equal the square root of negative 2me over h bar squared. And once again, I'm doing this because energy is negative, so the two negatives will cancel out. The resulting solution for this is then just going to be, instead of a complex exponential or a sinusoid from before, this is just going to be a standard exponential. So the general solution for this is just psi of x equals ae to the negative kx plus be to the kx. And remember, this is in contrast to if energy was always positive, because if energy is positive, then there's going to be a negative k squared at the front, and k is going to be positive square root 2me over h bar squared. In that case, we get complex exponentials or sinusoids. In this case, because the k is going to end up being, there's no negative sign here, and k is a constant, so instead this gives us exponentials, just instead of complex exponentials. And we just have to sort of look at the conditions. So first off, we're analyzing only when x is less than 0. So if x is less than 0, well, that means x is always going to be negative. Instantly, that means this term is going to blow up to infinity. So automatically, we require that a has to equal 0, and psi of x has to equal be to the kx when x is less than 0. Similarly, we can look at x is greater than 0, And the method for solving this is the exact same. The setup is exactly the same. We're still going to end up with d2 psi over dx squared is going to equal k squared times psi, where k is equal to square root of negative 2me over h bar squared. And this is going to give us the exact same exponential solution. Psi of x is going to equal, and we're going to, let's do like e and f, or f and g. So like, this is going to equal like f e to the negative kx plus g e to the kx, where x is greater than 0. And here, the opposite happens, where this g term is going to go blow up to infinity as x goes to infinity. So automatically, we require that g has to equal 0. So that means psi of x has to equal g times e to the kx when x is greater than 0. So what we have now is this piecewise function, where psi of x is equal to be to the kx when x is less than 0, and my apologies, I just realized I wrote this wrong. G is 0, so the one that's non-zero is f, so it's f e to the negative kx, and this is it's going to equal f e to the negative kx when x is greater than 0. And immediately, the next thing we need is we impose the condition that psi of x is continuous, because it doesn't make sense for it not to be continuous. Because once again, psi of x is a probability density. It doesn't. If it wasn't continuous, then you would have like an integral that goes to infinity for normalization, which doesn't work. So psi of x has to be continuous. So if we look at this, the point of discontinuity is at x equals 0. So at x equals 0, this exponential, both exponentials just go to 1. So what we have left is that b has to just equal f. Otherwise, psi of x won't be continuous. So psi of x is actually equal to, and let's just say that they're both equal to b. So b times e to the kx when x is less than 0, and then b e to the negative kx when x is greater than 0. So if we graph this out, you know, what this is going to look like is it's just going to be an exponential decay on both sides of the y-axis. So it's going to look something like this, where you have an exponential decay that goes out like this, and you have an exponential decay that goes out like this.
Right. So we have our wave function, and we know what it looks like, but there seems to be a slight problem. And the problem that I'm referring to is that earlier back in either the start of chapter 2 or like near the end of chapter 1, one of the things that we sort of stated was that psi had a few conditions that it had to meet in order for it to actually be a realizable wave function. The first condition is that psi has to be continuous. And this is, you know, something that we sort of know. It's something that, like, it makes sense intuitively that psi has to be continuous, because if there was a break in the wave function, then it wouldn't really be able to represent a probability, because its integral wouldn't actually exist. It wouldn't be possible to take an integral of mag psi squared from a to b if there's some sort of discontinuity in the middle. So psi is continuous is sort of intuitive, and that's okay. The second point that we sort of made, and this is one of the requirements to solve one of the problems back in chapter 1, I think, was that the derivative of psi also had to be continuous. And I don't believe we actually proved this. If I remember correctly, I think this was just sort of given, and sort of we sort of said, like, you know, it sort of makes sense that psi would have to be smooth as well, because but like we didn't really give a solid proof for this. And it turns out that this isn't necessarily the most general form of this condition. We're actually going to prove this now, and we're going to see that the more general form for this is that the derivative of psi does have to be continuous, except when the potential v is infinite, either positive or negative infinite. So I suppose it would be better to write it as plus minus infinity. And in this case here, remember that our potential is a Dirac delta well, with the well at x equals 0. So the potential is negative infinity at x equals 0. So this condition isn't technically violated. Now, what we're going to do is we're going to actually prove this. So to prove this, we're going to start with the Schrodinger equation. So we have negative h bar squared over 2m times d2 psi by dx squared. And this is getting added with v times psi of x and then this is equal to e times psi of x. And just to make it extra clear, v also has x dependency, so I might as well write it as v of x. Okay, so the way that we prove statement 2 is we start by taking an integral from two arbitrary points, and let's call them negative epsilon and positive epsilon, and we want to see what happens sort of as we take the limit where epsilon goes to 0. So if we do that, the equation we're going to get is going to look something like negative h bar squared over 2m, and then we take the integral on both sides, so negative epsilon to positive epsilon, d2 psi by dx squared dx, plus the integral from negative epsilon to positive epsilon, v of x psi of x dx is going to be equal to e times the integral from negative epsilon to positive epsilon psi of x. So immediately, this term right here is just going to be equal to d psi by dx evaluated from negative epsilon to positive epsilon. This can sort of be rewritten as just delta d psi by dx. So what is this? This is just sort of the change in the derivative as we go from, you know, negative epsilon to positive epsilon. If we take the limit where epsilon goes to 0, what this is basically a determinants of sort of continuity. If this value turns out to be 0 when the limit of epsilon going to 0, then the derivative is continuous, because what that means is that at the instantaneous change from the point directly to the left of 0 and directly to the right of 0, which is negative epsilon and positive epsilon, in the limit that those go to 0, the derivative has a change of 0 across that range. So that is literally just the definition of continuity. If it's non-zero at the limit where epsilon goes to 0, in that case, it's going to be discontinuous, because in that case there is some finite jump in d psi by dx, in which case we have discontinuity. So let's write this out. So negative h bar squared over 2m times delta d psi by dx plus the limit as epsilon goes to 0 of the integral from negative epsilon to epsilon v of x psi of x dx is equal to the limit as epsilon goes to 0 of e times the integral from negative epsilon to positive epsilon psi of x dx. And I didn't close this off with the dx. I'm sorry. And instantly, first off, this term is just 0, because as the limit of epsilon goes to 0, we have an integral of 0 to 0 of some function psi of x. And this is a well-behaved function that doesn't have any crazy properties. So instantly, this just equals 0. Standardly, when v of x typically is also a well-defined function, and what will happen is that most of the time, this term right here also goes to 0. Because if v of x is just some normal function multiplied onto a well-behaved function like psi of x, there's nothing wrong. We get another well-defined or like well-behaved function, and as we take the integrand limits to 0 and 0, that's just going to give us 0. However, this is where sort of the unique case comes in, because remember, v is equal to negative alpha, and then multiplied by a Dirac delta of x. So if we write this out, negative h bar squared over 2m delta d psi by dx is, and I'm going to move this around to the other side. So this is going to equal negative the limit as epsilon goes to 0, integral from negative epsilon to positive epsilon, and we have negative alpha times Dirac delta of x times psi of x dx. So what's happening? Because if you look at this, remember that sort of one of the properties of a Dirac delta is that it sort of carries out or it like snipes out a specific value of psi of x. Because one of the properties we had was that the integral from, you know, negative infinity to positive infinity of, you know, Dirac delta of x minus a times f of x dx pulls out f of a. So what happens here is that it's gonna just pull out psi of 0. So if we look, we have negative h bar squared over 2m times delta d psi by dx, and this is going to equal, the two negatives make a positive, and we have alpha times the integral of delta x psi x, which is going to pull out psi 0. So the change d psi by dx is then going to be equal to negative 2m alpha over h bar squared times psi 0, and specifically in our case, psi of 0 is just equal to b, so this is actually equal to negative 2m alpha b over h bar squared. And what this is saying is that the derivative of psi with respect to x has an instantaneous change as we go from the left side of 0 to the right side of 0 of negative 2m alpha b h bar squared. And if we look at this, that seems to make sense because it's increasing, derivative is positive, and then it gets to the origin and it instantaneously changes to negative. So, that physically that makes sense, and also mathematically we've sort of shown that in the case of v being like an infinite potential, such as a Dirac delta, the derivative of psi isn't necessarily continuous. But when v is finite, when this is any sort of finite function, as the integrand of negative epsilon and epsilon has epsilon go to 0, this integral also cancels out to 0, and we get that this term is just equal to 0. So in normal cases, d psi by dx is indeed continuous, but in special cases where we have infinite potentials or Dirac deltas, that sort of breaks down, and we get these sort of weird looking functions with derivatives that aren't necessarily continuous. All right, now to finish everything up, let's do a quick wrap up. So we have the definition for psi of x, we have what the derivative of psi of x looks like, we have the definition of k, and we have this requirement that the derivative of psi with respect to x has to be discontinuous by this amount. So we can link this to k, and we can actually find the general formula for the energies if we recognize sort of what this term looks like at the border. So at x equals 0, what happens is d psi by dx at sort of x equals 0 is going to give us, so at 0 we have bk when approaching from x negative, and we have negative bk when approaching from x positive. So the jump d psi by dx at x equals 0 is evidently equal to just let's see, so we go from negative to positive, so it's negative 2 bk. This is going to equal this, so we can link these two together and get a formula for k. So 2bk is then going to equal 2m alpha b over h bar squared. We cancel out the 2b, then k is equal to m alpha over h bar squared. We also have sort of the definition for k here, so this is going to equal square root of negative 2me over h bar. And from here, we can find the values of energy. So we cancel out one of the h bars, and we square everything. So negative 2me is going to equal m squared alpha squared over h bar squared. E is going to equal negative, let's see, m alpha squared over 2h bar squared. And once again, we see that, we defined energy but negative initially, and energy here is indeed also negative. And now we finally can sort of normalize b, and then we'll have the full general wave function. So we have the integral from negative infinity to positive infinity of mag psi squared dx, and this is going to equal, because we have what psi of x equals, so this is going to give us like 2 magnitude b squared times the integral from 0 to infinity of e to the negative 2kx dx. So what I'm doing here is that because of the fact that there's a discontinuity and we have like sort of a piecewise function, I'm combining them together because I'm recognizing the fact that there's sort of symmetry about the y-axis, so I can just look at one side. So for example, in this case, I'll just look at e to the negative kx, and then I'll just multiply it by 2 after integrating from 0 to infinity because of the symmetry. So I can just look at this, have this nicely behaved exponential that goes to 0, and then just be done with it. So we do this, we sort of, and then we set this equal to 1, and what we're going to get once we evaluate out this, let's see, so this is going to be 2 magnitude b squared, and then we have negative 1 over 2k e to the negative 2kx, going from 0 to infinity, and this is equals to 1, so magnitude b squared times what? This is going to be negative 1 over 2k multiplied by, infinity is just 0, subtracted by 1, so this is positive, and this is equal to 1/2, so magnitude b squared is going to equal the k, so b equals the square root of k. Yes. Okay. And we also know what k equals. Earlier we defined a nicer version of k in terms of constants. So this is just equal to square root of m times alpha over h bar. Now we can sort of write everything out. So because remember psi of x is equal to, well, I don't have to write this out. I can just copy paste it. Because we have this behavior for psi of x. So we plug everything in for b, then we're just going to get that this is equal to square root of m alpha over h bar e to the kx when x is less than 0, and square root m alpha h bar e to the negative kx when x is greater than 0. And we can actually write this out further and condense this into a single equation by taking advantage of sort of magnitudes. And to do that, I'm going to start by sort of making my, I'm going to make my height a little bit larger here because I'm running out of space. Okay, let's take this and move it down here. Okay, so what I mean by this is that we know that k has sort of this form. So, you know, k is equal to like m alpha over h bar squared. So if we write this out fully, then what we get is that this is equal to piecewise going square root m alpha over h bar, going from e to the power of m alpha x all over h bar squared when x is less than 0, and square root of m alpha all divided by h bar times e to the negative m alpha x h bar squared when x is greater than 0. And what we can do is we can just sort of use an absolute value to express this. So there's nothing stopping us from just writing psi of x as just like, you know, psi of x is equal to square root of m alpha over h bar e to the negative m alpha magnitude x all over h bar squared, and defining the energy as negative m alpha squared over 2 h bar squared. Okay, now that we've looked at bound states, let's do the opposite and look at scattering states where energy is now positive. So if the energy is positive, we have the same setup as before. The only difference now is that k is going to have to equal square root of positive 2me over h bar. Because back then we put it as negative because energy was negative and the two negatives cancel out. But in this case, it cannot include the negative sign up here. So d2 psi by dx squared is actually going to equal negative k squared times psi. In this case, well, we've already encountered sort of this form of differential equations back in sort of free particle solutions. So we know the general wave function solution for this is going to be psi of x is equal to a e to the I kx plus be to the negative I kx, because yeah, remember that we're using complex exponentials here because we're dealing with scattering states, whereas if we were dealing with bound states, this sort of function would be instead represented as sort of a sinusoid, sine x plus cosine x, etc., etc. Now the big thing here is that once again we have to analyze both sides of the well. Because if this is our well, with our Dirac delta potential, what happens is that we have this point at x equals 0 where the potential goes to negative infinity, but v equals 0 everywhere else. So what we have to do is we have to sort of treat the wave function at x less than 0 and at x greater than 0 separately, and then we have to sort of joint them together as we did before. So let's suppose that this is equal to when x is less than 0. So that means when x is greater than 0, we have sort of the exact same system, but just with different constants at the front. So this is going to be f e to the ikx plus g e to the negative ikx when x is greater than 0. So psi of x is going to end up equaling a piecewise function just as before. Now, to actually join these two together, to start sort of solving for these constants, we can start employing sort of the boundary conditions that we have. The first one is that psi is continuous. And sort of the joining point is at x equals 0, where all the exponentials equal 1. So what we have is that condition 1 is really telling us that a plus b has to equal f plus g. Now, we have condition 2 from back when we were looking at bound states, which is that sort of the derivative of psi has to be continuous except where the potential equals 0. Except where the potential is infinity. And when the potential is infinite, the discontinuity in d psi by dx is specifically equal to the negative of 2m alpha divided by h bar squared times psi of 0. So what we can do is we can find this manually by sort of deriving out our piecewise function, and we plug that in and we get a new condition in terms of a, b, f, and g. So if we do that, then what we get is that d psi by dx is also going to be piecewise, and it's going to be ik times a e to the ikx minus be to the negative ikx when x is less than 0, and then we have ik times f e to the ikx minus g e to the negative ikx when x is greater than 0. And what we want is the sort of differential sort of, or the discontinuity in the derivative at sort of our point where v equals 0, which is when x equals 0. So if we say that, then d psi by dx evaluated at x equals to 0 is going to give us ik a minus b when x is less than 0, and ik f minus g when x is greater than 0. So then we just take this term and subtract by the top term to get the difference. So what this is going to give us is ik, let's see, f minus g minus a plus b is going to equal negative 2m alpha over h bar squared, and then psi of 0 can equal two different things, because remember, psi is a piecewise function, so we can either define it as a plus b or we can define it as f plus g. It doesn't really matter. All that's going to change is like which of these sort of coefficients at the front, f, g, a, or b, that we solve for first. For the sake of just following Griffiths' derivation, we're just going to replace it with a plus b. And if we do this, what we can do now is we can solve for f and g in terms of a and b. So if we do that, then what we get is that f minus g minus a plus b. We're going to start by taking the ik and moving it over to the other side, so 2m alpha over ik h bar squared multiplied by a plus b. Then we can move the a's and b's to the other side. So this is going to give us f minus g is equal to negative 2m alpha ik h bar squared times a plus a minus 2m alpha ik h bar squared b minus b. And if we rewrite this, we can get that f minus g is equal to, let's see, a times 1 minus 2m alpha over ik h bar squared, and then subtracted by b times 1 plus 2m alpha over ik h bar squared. And at this point, to make this a little bit nicer to look at, we're going to introduce a new variable. We're going to call it beta, and beta is going to be specifically defined as m times alpha over h bar squared k. And the reason why we're doing this is because these are all just a bunch of constants. There's nothing wrong with us just sort of condensing them all into a single constant beta. So we do that, then f minus g is going to equal a times 1 minus 2 over I multiplied by beta, subtracted by b, multiplied by 1 plus 2 over I, multiplied by beta. And then, for convention's sake, we always put imaginary values and the numerators, so what we really have is f minus g is equal to a times 1 plus 2i beta, subtracted by b times 1 minus 2i beta. and that is sort of our condition 2. Okay, this next part is a little bit tricky, so I will sort of try my best to elaborate on this a little bit, because I feel like Griffiths doesn't really explain this as well as he should. But basically, we have this piecewise wave function here, and we have 2 conditions. So there's a bit of a problem here. And the problem is that our wave function here is defined in terms of 5 variables. We have A, we have B, we have F, we have G, and we have K. We only have 2 sort of conditions for solving our system of equations. So normally, when you have a system of n variables, you typically also need n corresponding constraints in order to actually solve the corresponding system. We only have 2 for a system of 5 variables. So obviously we don't have enough information to actually solve for A, B, F, and G respectively. Now, the second problem comes about, which is that traditionally, if we didn't have enough conditions, or if we didn't have enough constraints in a quantum mechanical problem, the first thing we would typically do is start doing normalization in order to impose additional constraints. Because, you know, that's a really easy thing to do. We can say, okay, the integral from negative infinity to infinity of max I squared has to equal 1 by necessity. The problem is that we're dealing with scattering states. And as we sort of found earlier on in the prior section, scattering states will always, not just necessarily, but scattering states by definition do not have normalizable wave functions. So it isn't a valid strategy for us to actually try to normalize and impose additional constraints onto the system. Instead, the actual way to solve this sort of involves looking at this more intuitively and sort of finessing out a few additional constraints that mathematically we wouldn't have been able to do. So what I mean by this is that if we look at the form for these equations, what we see is that these are traveling waves, right? Each of the ikx is a wave traveling from left to right. Each of the negative ikx represents a wave traveling from right to left. Obviously, there's no vt term, but that's sort of implied in the phi of t that's attached onto psi of x. So this term and this term represent waves traveling to the right, and these 2 terms represent waves traveling to the left. So if we were to draw this on our potential sort of graph, we have our Dirac delta potential that goes, to negative infinity. This is a very messy drawing, I'm sorry. Something like this. What we would have is, we have, because this is to the left, so what we have is a positive wave going to the right, so AE to the IKX, and we have a negative wave going to the left, BE to the negative IKX, and then we have a positive wave going to the right, FE to the IKX, and then we have a wave going to the left, GE to the negative IKX. So hopefully you've taken classical mechanics and you've taken wave motion, because this should instantly sort of stand out as sort of almost perfectly analogous to sort of the idea of a wave traveling across a different medium / boundary. And what I mean by this is, why is my colors not changing? Okay, whatever. What I mean by this is that in sort of classical mechanics, when you started learning wave motion, what we found was that if we had something like what is happening with my, there we go. If we had something like a string and it's connected by a knot onto like a second string that has a different mass index, so like maybe this string is denser or this string is less dense, what'll happen is that if you have like a wave that's traveling on this string and it's going this way, once it reaches this boundary, what'll happen is that depending on depending on what the actual materials are for depending on what the actual materials of the string are, you can have different possibilities. Either the incoming wave, so the incoming wave comes this way, it'll either get reflected backwards going this way, or it could get reflected backwards with like sort of the amplitude becoming negative instead, or it can make it through and it can go through the medium and start traveling on this new string instead. So there's 3 possibilities. Either once it makes it here, either it gets reflected backwards with a positive amplitude, so this way, or it gets reflected backwards with a negative amplitude this way, or it makes it through the intersection and it keeps on going through this new medium. Oftentimes both happen simultaneously, where part of the wave gets through into the other medium and the other part gets reflected back, either as a positive amplitude or a negative amplitude, depending on the properties of the string. So if we look at sort of this from sort of the same standpoint, what this represents is basically a particle. It travels in from the left, which would be represented by AE to the IKX, and it either gets reflected and therefore is sort of described by BE to the negative IKX, or it makes it through this potential barrier and becomes FE to the IKX. Similarly, if we had a particle coming in from the right instead of the left, then GE to the negative IKX would define this particle as it comes in. It either gets reflected and therefore is described as FE to the IKX, or it makes it through and becomes described as BE to the negative IKX. Either way, one of these two, either A or G, is equal to 0. And that depends on whether our particle is coming in from the left or coming in from the right. So by convention, we define scattering setups like this with the particle coming in from the left. So automatically, we can sort of imply that G is just equal to 0. So this is what I mean by this is sort of, we're finessing out an additional constraint. Because sort of we're implying that G equals 0 because we sort of recognize that this is a scattering setup, or so sort of a particle scattering setup, so we can define either A or G equal to 0. Nothing in the math tells us that we can do this. This isn't something that the math allows us to do. It's something that we can sort of intuitively sort of impose onto this system because we recognize it as a sort of a scattering problem. So we're going to impose condition 3, which is that G is going to equal 0 because we're only going to analyze sort of particles coming in from the left instead of particles coming in from the right. So if we do that, what happens? We sort of shove G equal to 0 into these above constraints, and what we have left is, first off, F equals A plus B, and then second off, F is equal to A 1 plus 2IB minus B 1 minus 2IB, or beta. Apologies, not B, beta. And this is sort of our new constraints. These are our new constraints, and this is much nicer now because assuming that for now we ignore K, this has been reduced to sort of a system of 3 variables that only use it, that has 2 constraints, which is much nicer compared to before where we had 4 with 2 constraints. Okay, so this next part is sort of what I would consider the trickiest part of solving the scattering states. And it's recognizing the fact that we can actually decompose this into 3 separate wave functions. So what I mean by this is that we have, our potential well that looks something like this. And what's happening physically is that there's a particle and it's moving forward with some velocity v. And based off of this setup, what happens is that this particle reaches, this well, and there's 2 possible outcomes. Either in case 1, the particle gets reflected, in which case you have sort of a particle that is going this way now with speed v, or in case 2, it makes it through this barrier, and you now have a particle going this way with speed v. So what we can sort of do is we can recognize that these are 2 separate wave functions, not 3. Apologies, I said that wrong. This is 2 separate wave functions, and it's instead of it being separated, because earlier on we have this piecewise function that's separated from x less than 0 and x greater than 0. So this is a piecewise that's defined in terms of when we're to the left of the well and when we're to the right of the well. There's another way to recognize it, and we can sort of recognize the wave function as sort of prior to running into the well and afterwards. So prior, we're defined purely in terms of AE to the IKX. And then afterwards, we're defined as a mix of BE to the negative IKX and FE to the IKX. So before, we're defined with the incoming particle, AE to the IKX. And then after, we're defined using BE to the negative IKX plus FE to the IKX. And remember, wave functions are probabilities. So
what's really happening is that, you know, the particle has, so this is going to be normalized. The particle has some probability of, you know, it has a 100% probability of being, like, moving towards the well before. And then afterwards, it has a probability B of either getting reflected or a probability F of making it through. So these coefficients sort of are what modulate the probability of either the particle making it through the well or getting reflected back, where B is the one that modulates sort of how likely it is for the particle to get reflected, and F is the one that sort of modulates how likely it is for the particle to make it through the well. So what we can do here is we can take advantage of relative probability. So what I mean by that is that we can enforce this idea that the magnitude of a squared is actually equal to the magnitude of b squared plus the magnitude of f squared. Because remember, ultimately these are cosines and sine functions, and they have amplitudes of 1. They're modulated by b and f. So b and f are what actually determine, shall we say, the probability. The magnitude squared of these terms are what actually determine the probabilities, the corresponding probabilities. And that's sort of why I say that we can look at this as like 3 separate wave functions instead of 2. Is that there really is 3 different wave functions. There's the wave function of the particle as it sort of makes it, as it's coming in from infinity. There's the wave function of the particle as it gets reflected, and there's the wave function of the particle as it makes its way through. So what we actually see is that, you know, that obviously magnitude a squared is going to be 1, because that's the full, how do we say this? It's the full probability of the particle as it comes in. And then it sort of, the probability splits between b and f. It either sort of gets reflected back or it makes it through. It doesn't do both. But sort of the wave function has to include both, because the whole idea of the wave function is that it represents probability. So both of these terms get represented in the wave function, but their magnitude squareds are what the actual probabilities are. So we can impose this sort of condition that the magnitude a squared is equal to magnitude b squared plus magnitude f squared, because these are the actual probabilities. So instantly, what I can do is I can divide everything by magnitude h squared and say, okay, there's a 100% probability that the particle either gets reflected or makes it through. So the way I say this is 1 is equal to magnitude b squared over magnitude a squared plus magnitude f squared over magnitude a squared. And what this is saying, once again, is that, okay, there's a probability, this is the probability that the particle gets reflected, and this is the probability that the particle makes it through the well. So we actually have names for these. This is called R, and this is called T, and they're called the reflection and transmission coefficients, respectively. So what we have here is we have B and A, we have F and A, and we have these 2 conditions that are described in terms of F, A, and B. So we can sort of redefine these coefficients in terms of like this beta variable by sort of playing around with conditions 1 and 2, and that's exactly what we're going to do. Okay, so since these both have the common trait of being divided by mag h squared, let's define b and f in terms of a. So if we do that, what we're going to get is, let's see, f minus b equals a, first off, and then we have this condition 2, so we can plug that in and solve for b instantly. So what we have is that a times 1 plus 2i times beta minus b 1 minus 2i beta, and then minus b is equal to a. So what does that give us? Let's see. I'm gonna move the negative onto the other side. So this is gonna be b 1 minus 2i beta plus b is going to equal a 1 plus 2i beta minus a. So what we have then is b times, what is that? 2 minus 2i beta is equal to a times 2i beta. So we have b is going to equal I beta over 1 minus I beta multiplied by a. And then if we plug this back into f, so this is going to give us f is equal to a
plus b, which is plus I beta 1 minus I beta times a, or f is equal to 1 minus I beta, and then, let's see, 1 minus I beta over 1 minus I beta, so a minus I a beta plus I a beta is going to be 1 over 1 minus I beta times a. If we plug these into our reflection and transmission coefficients respectively, we're going to get R is equal to, let's see, magnitude b squared over magnitude a squared. So that's going to give us IB, or I beta, times negative I beta, divided by 1 minus I beta times 1 plus I beta. And then we have magnitude a squared divided by magnitude a squared, so those just cancel out to 1. This is going to give us beta squared divided by 1 plus beta squared. Similarly, the transmission coefficient is going to give us magnitude f squared divided by magnitude a squared. This is going to give us, let's see, 1 over 1 minus I beta, 1 plus I beta, and then the magnitude a squares at the top and bottom both cancel to 1. This is going to give us 1 over 1 plus beta squared. So these are correspondingly the probabilities, effectively, of either the particle getting reflected back after making it across the well, or sort of managing to actually transmit across the well to the positive side. So next, we can define these by actually defining beta, because we know that beta equals m alpha over h bar squared k. And if we do that, then what we're going to get is that R is equal to m squared alpha squared over h bar fourth k squared over 1 plus m squared alpha squared over h bar fourth k squared. And that's going to give us, what, m squared alpha squared over h bar fourth k squared plus m squared alpha squared. We can do it again and do 1 over 1 plus h bar fourth k squared over m squared alpha squared. And then we can redefine k, because remember that k itself was a variable in terms of energy, right? So k is equal to square root of 2me over h bar, as we've defined earlier. So k squared is going to equal 2me over h bar squared. So this is going to give us 1 over 1 plus, let's see, h bar squared, 2 h bar squared e over m alpha squared. Is that correct? Yes. And then we can do the same for t. So we can do t is going to equal, this one's a lot easier, 1 over 1 plus beta squared, so plus m squared alpha squared h bar fourth k squared. So 1 over k squared is going to equal h bar squared over 2me. So this is going to equal 1 over 1 plus 2m cubed alpha squared over h bar squared, excuse me, h bar squared times sorry, I did this wrong. This is going to equal m squared alpha squared h bar fourth times h bar squared over 2me. So this is equal 1 over 1 plus m alpha squared over 2 h bar squared e. Yes. Okay, so what we see then is that sort of E is the only thing that matters. It's the energy. Everything else is a constant. When we see that if energy is really high, then this term has the denominator become really big. The reflection coefficient goes down to 0, whereas the transmission coefficient has this term go to, as e goes to infinity, goes to 1. So as the energy gets larger, the probability of the particle making it through the well becomes larger, and the probability of the particle being reflected back becomes smaller. And the same thing is, the opposite is true as the energy goes down. So at lower energies, it's more likely for the particle to not make it across the well and get reflected backwards instead. Okay, so the final thing that we still haven't sort of recognized is that, once again, we have this idea that scattering wave functions are not normalizable, therefore the stationary states are not physically valid. However, the resolution to this is still the same as before, in that we can sort of form linear combinations of these non-realizable states to get a general wave function that is normalizable, because we did the whole sort of Fourier transform stuff back in chapter 2.4. The problem here is that the math for doing it for these delta well functions actually gets very, very complicated very easily. So much so that it's just generally more practical to just hand these problems to computers instead of actually doing them by hand. Luckily, I don't believe that Griffiths is going to make us do any of those types of problems by hand, so we can just sort of recognize that it is possible to get physically realizable states via Fourier transforms in this case, in the same way that we did in 2.4. And we're just not going to actually go through with doing that, because I believe that 9 times out of 10, those problems are just straight up impossible without brute forcing with a computer. The other thing, one other thing before we're done with this, is that we can also look at sort of the delta barrier instead of the delta well. So what I mean by that is that we can reverse the sign on V, and we can get a barrier that goes up to infinity instead of a well that goes down to negative infinity. And sort of the method for solving this is the exact same. The only difference is that V, instead of equaling, negative alpha Dirac delta of x, it goes to just positive alpha Dirac delta of x. And that's just a matter of reversing the sign on everywhere that alpha actually appears. That's not too bad. And sort of the more interesting thing is that actually the transmission and reflection coefficients aren't affected at all, because if we look at these are based off of alpha squared, not alpha. So by changing the sign, we actually don't do anything. The probability of a particle making it through a barrier versus a well is pretty much the same thing. There really is not a difference. So these two sort of situations, there's not enough difference between a delta well versus a delta barrier to actually be worth it to solve this whole thing all over again. Because ultimately, the biggest important thing, which is the transmission and reflection coefficients, are unchanged, and everything else sort of is trivial as well. There's just some trivial sign changes here and there, but ultimately the results are still the same. So therefore, this is really just something that we can note in passing. And with that, we are done with the delta function potential.